So in the last video, we talked about the basics of vectors, and I kind of introduced that we can write a vector with just how far do we move to the right or horizontally, um, and how far do we move up or down vertically. But vectors are from something that we call linear algebra, which genuinely is just meant to represent algebra on lines, so algebra on vectors. So we want to do our basic algebra type stuff on our vectors. So what are our operations from algebra? Well, we can add things together. So I want to talk about what it means to add two vectors. And we can also multiply things together. So you may think we're going to multiply two vectors together. And that's something from chapter 16, which we actually don't have a chance to get to this semester, but it turns out you can multiply two vectors together. And actually you have two different ways, which is why it gets confusing. But the point is we're not going to do that for our class. So instead of multiplying two vectors together, what we are going to multiply together is a number times a vector. And we're going to talk about what adding two vectors does and what multiplying a number times a vector does. Well, let's look at the xy plane here. And let's say, I'm wasting a lot of space drawing like that. Let's say I have a vector here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's say I have the vector v is 2, 4, and w is the vector 3, 1. Yeah. So I can draw v. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So our vector v goes to the right 2 and up 4. So we end right there. And this is our vector v. And our vector w goes to the right 3 and up 1. So ends just right there. Right there. Great. Well, now when we add two vectors, if I wanted to add vector v plus vector w, well, you can kind of think of this in two different ways. And let's think of it with the component form first. Well, now to do vector v plus vector w, the most natural way to do it would just be, well, to go to the right 2, then up 4, then to the right 3, and up 1. But really, it doesn't matter the order, going up to the right or going right and then up, or do all of our right motion and then all of our up motion. So really our end result would just be go to the right 2, up 4, then to the right another 3, and then up another 1. So when we add our vectors, we just add the component forms. So this resulting vector would just be 5, 5. This is like saying I say go this far first and then go this far second. Then we end up at the vector 5, 5. So let me draw our vector 5, 5. Well, we go up 5 over 5. That is this point right here. Great. So we can kind of see that definitely this vector v plus w does kind of look like it's made up of v and w. Like, sure, um, looking at this graph, we can kind of tell it's like, yeah, it's halfway between v and w, and it's like the kind of sticking between them there, real interesting. Well, what happens if I literally just take my vector v and stick it on the end of vector w? So again, we do our stuff from v, then let's do our stuff from w. So let's take my vector w and stick it on the end of vector v. Well, so vector v says I go to the right 2 and up 4. And then once I'm right here, vector w says I go to the right 3, so from 2 to 5, and up 1, so from 4 to 5. And yeah, we end up at that exact point. This is just the geometric version of exactly what we wrote right here. Well, again, when we add two things together, does the order matter? And in our experience, we say no. 2 plus 3 is 3 plus 2. So vector w plus vector v should be the same as v plus w. The order that we do these things in doesn't matter. So now let's do this graphical version of this. Let's go out by vector w and stack vector v on top of it. And yeah, it absolutely ends at that exact same spot. But maybe this gives us a little bit of a better picture of what v plus w represents geometrically. So this is a shape that we made between our two vectors with v and w, and then stacking w on v and v on top of w. So this is a shape with 4 sides where opposite sides are parallel. And in this case, we call that a quad for 4 sides and lateral, quadrilateral. That is this kind of shape. And how do we describe v plus w? That is the diagonal of the quadrilateral. Is the line that goes from here to here. Now, technically, we have another diagonal, and that is the one that goes from this point to this point. But v plus w is that longer diagonal. So two diagonals are always going to be either they're the same size or one of them is bigger than the other. And v plus w would always end up being the bigger diagonal there. I believe so. Either way, it is this vector in the shape. So that's kind of the geometric interpretation of adding our two vectors together. But literally speaking, when we add two vectors together, we are just adding the x's and the y's. So what is the vector 3, negative 4 plus the vector 0, 2? Well, 3 plus 0 is 3. Negative 4 plus 2 is negative 2. We just add the components. It is that straightforward. Well, let's talk about the length of this vector in comparison to the individual parts. So there is something called the triangle inequality. And to understand that, let's look at some numbers that we can come up with here. So let's say that we want to talk about the distance from 0 or the size of some numbers. So let's say I have negative 2 plus 3. And let's take the absolute value of that. But we do negative 2 plus 3, and that turns out to be 1. And the absolute value of 1 is just 1. Well, what if I took the absolute value first and then added the numbers? the absolute value of -2 is, of course, 2. The absolute value of 3 is 3. So 2 plus 3 is 5. So in this case, which is bigger or smaller, the absolute value of the whole thing or the sum of the absolute values? Well, 1 is certainly less than 5. So in this case, -2 plus 3, the absolute value of -2 plus 3 is less than the absolute value of -2 plus the absolute value of 3. Well, what if we didn't have this negative right here? Well, then I think we clearly see instead of 2 plus 3, this would be, sorry, instead of -2 plus 3 giving me 1, 2 plus 3 would have just given me 5, whose absolute value would have been 5 still. So in this case, they would be equal. And it turns out that if we have x squared plus y, x plus y, this absolute value is always going to be, comparing against the absolute value of x plus y, less than or equal to the absolute value of x plus the absolute value of y. And this is what we call the triangle inequality. And this feels like something new, but once we look at the vectors, I think we're going to see that it is actually something that is very normal and reasonable to us. Well, let's say that we're looking at our vectors here. Again, vectors don't really have absolute values, they have magnitude. So we can talk about the magnitude of our vectors to talk about their length. Well, let's look here. The length of v plus w versus the length of v, so going here, plus the length of w. Well, if we're doing the exact same kind of triangle inequality, then all we're saying is that the length of v plus w is less than or equal to the length of v plus the length of w, aka the length to go straight across is shorter than to go around and over. So the example that I like to give with this is like, say that you are like walking along these sidewalks trying to get to your car. Right, you're a person here and your car is somehow magically parked on the sidewalk, maybe. I'll draw a Volkswagen Beetle. It's a bad Beetle, but yeah, we get the idea. So we're parked right there. Is it shorter to walk straight across the grass or to go down to this sidewalk and then down to this sidewalk? And I think we know it's shorter to just walk straight there, which is all the triangle inequality is saying. And now, based on this shape, can we tell why it's called the triangle inequality? I think so. Now, why is it less than or equal to? Well, what if one of the sidewalks was like 0, for instance? So if this sidewalk was here, but then this sidewalk was the 0 sidewalk, so actually not that far apart at all. Then can you really say that walking straight there is shorter than walking along the sidewalks? Well, in this case, no, walking straight there is the same length as the sidewalks. Now I drew these as if they were right triangles, but sometimes they're even not. So what if the sidewalk was like this and then this? Well, then now is it shorter to go straight across or along the sidewalks? It is still shorter to go straight across. So they'll, which in this case, this would be this diagonal, which is the sum of the vectors, is shorter than to go one sidewalk than the other sidewalk. So that is the triangle inequality. And this is powerful. This is cool. This gets used in like real analysis all the time. It's very important and neat. I mean, for our sakes, it doesn't feel immediately important, but for the larger world as a whole, it is very important. It gets used a lot. And I think that we use this a lot. You know, if you're walking along here, this is just some grass field that you don't mind walking across, and your legs are sore. Are you going to walk straight across? Probably, because you want to not have to be walking so long if your legs hurt. So I think this is actually gets used all the time by all of us in our daily lives, unless you have like really strong calves or something and you don't mind walking forever and ever. But good for you, I guess. Anyway, this is our trial inequality, and it's very powerful and very cool. Well, the next thing to talk about would be this thing here. So we talked about adding vectors, two vectors together. And we talked about the triangle inequality, comparing the lengths of adding two vectors together. But let's talk about how we can multiply a real number times a vector. So let's say we have our vector 2, 4 from up here. But we wanted to multiply that vector by a real number 3. What would make this the easiest operation that we could do? If I'm wanting to stretch this vector out, if I'm wanting to add this vector to itself 3 times, well, that just turns into 3 times 2 and 3 times 4. So 6 and 12. Well, graphically speaking, we take this vector and we stick it onto itself 3 times. That is just genuinely making it 3 times as long. So multiplying a real number times a vector just scales that vector. You know, we say scales to say like stretch, so like it scales it by a magnitude of whatever. So it scales the vector by a factor of 3 by the real number. So to that end, instead of calling these real numbers in the context of vectors, we call these scalars because they scale the vector. Very good. Well, now we can scale a vector by a real number. And it turns out if we have a vector v is x comma y, then r for our scalar times v is just rx, ry. And we call this scalar multiplication. Very good. Now, the last thing that we can talk about is how scalar multiplication interacts with the magnitude, maybe. Well, so let's say I have my vector v is 3, 4. Then the magnitude of v we did from the last section. That's just the square root of x squared plus y squared, which in this case, x is 3 and y is 4. This turns into 9 plus 16, which 9 plus 16 is 25. So the square root of 25 turns out to be 5. So the magnitude of v is just 5. Well, what if I multiplied vector v by 2? What effect should this have on the magnitude? Well, graphically speaking, we're just doubling how long the vector is. We're making it twice as long. So literally, we are just making it twice as long. So by our intuition, we really want to say this. And it turns out this is absolutely true. We can just pull our scalars out to get this of the magnitude. Now, something happens kind of funky though if we had a negative scalar. So what if we have -2 times v? Well, now it doesn't really make sense to say our magnitude is -2 times 5. Because, well, how are we going to have a negative length? So this means we just take the absolute value of that instead. And that just turns into 2 times 5. So we can say for our magnitude, that the magnitude of r times v is equal to the absolute value of r times the magnitude of v. You're just making it twice as long for that example, but maybe if we have -2, we're also flipping that direction. So we want to put an absolute value there to let us know that our magnitude does have to be positive. Now, if we talk about the direction angle, then if I'm talking about 5 times the vector v, then how does making the vector 5 times as long change the direction at all? How does this direction compare to this direction? Well, that is the exact same angle between here and here, right? So the direction angle for this case turns out to not change at all. But what if I multiplied my vector by -5? Well, now instead of my vector looking like this, now I'm stacking it on itself 5 times, but also facing the opposite direction. So how do I figure out my new direction angle? Well, this difference is just going to be by 180. So if this ends up being a question of where we ask ourselves again stuff about what quadrant we're in. So we're in quadrant 1, all we really have to do is add 180. Well, really, no matter what quadrant we're in, we can just add 180. But I guess what I'm talking about now is we have to be careful about where we end up. So let's say, for instance, I have some vector. V has direction angle. Let's say 32 degrees. Well, then -v faces the opposite direction. And so for vector v, it just looks like that. That terminates in quadrant 1. So vector -v, I can just add 180. And get 212 degrees for that direction angle. But what if instead of 32, we were something like, let's say 97 degrees? Well, now when we add 180, And again, this puts us like in quadrant 2, which means this negative of the angle, or negative of the vector, is in here, which means this distance is another 180. So when we add 180, we get 7. 9 plus 8 is 17. So 277. And is 277 a good angle for us to worry about? Yeah, that's perfectly fine. But what if we had direction angle that was bigger than 180? What if our direction angle was 200 degrees? Now, our vector would be in quadrant 3, and we'd want to get something back in quadrant 1. So now we may want to subtract 180 degrees and get back to 20 degrees. And if we were in quadrant 4, the kind of same thing would happen. We would need to go back 80 degrees to get in quadrant 2. Sorry, 180 degrees to get in quadrant 2. So if we started in quadrant 1 or 2, we add 180. If we were in quadrant 3 or 4, we would subtract 180. From the direction angle to get the new direction angle. So this is, I think, it feels tricky, but it actually is not as bad as we think. And again, if nothing else, you can literally do like -3, 5. If we do the negative of that, then we can just do 3, -5, and then ask ourselves, well, what quadrant does this now sit in? And then do tangent inverse and do that mess to get the quadrant. But if we didn't know exactly what the vector looked like, this is still good stuff that we want to talk about. And again, here is the initial vector that I'm describing. So let's say original angle is in quadrant 1 or 2, add 180. If the original angle is in 3 or 4, minus 180. Okay, very good. So that is what I wanted to talk about for chapter 15 right away. There'll probably be a second video with a little bit more stuff, but I think this is a good stopping point for the video. A good stopping point may have been 20 minutes ago. This maybe should have been 2 videos, but either way, good job on your endurance. You should have taken a break maybe, but yeah.